Hi, hello, welcome. This is Discrete Mathematics, and today we're talking about section 2.4, Mathematical Induction. Before we get into this section, I want to talk a little bit about deduction versus induction. So deduction moves from general theorems, definitions, axioms, to something very specific that you want to talk about. Moves from general to specific. We've been using a lot of deductive reasoning so far. So an example of deductive reasoning would be the bus is scheduled to come at 8 a.m. on weekdays. Today is Monday. Therefore, the bus will come at 8 a.m. today. So that is deductive reasoning, using these general rules to apply to my specific case. Contrast that with inductive reasoning. So inductive takes a bunch of specific things that we're seeing. We're noticing this pattern of things, and we're going to form that pattern or all of those specific things into a general rule. So going back to our bus example, an example would be the bus has come late every Monday this month. Today is Monday, so therefore the bus will come late today. So that's taking a pattern of things that I've been seeing, the bus coming late, and making a general rule. The bus is going to come late today. So another example would be something along the lines of all the swans that I've ever seen are white. And I've seen over 100 different swans, so therefore all swans are white. So I'm taking these specific things or the specific pattern that I'm noticing, and I'm making a general rule about it. So today we're going to talk about mathematical induction. So suppose that I have a sequence of blocks numbered 1, 2, 3, 4, 5, etc. And they're sitting on this table. This table is infinitely long. Here's the dots because the blocks go on forever. Some of the blocks are marked with an X. You can see all the ones here in the picture have an X on them. And I'm going to suppose a couple things. I'm going to suppose that the first block is marked with an X. And then I'm going to suppose that for all n, if block n is marked, then block n plus 1 is marked. So if I have a block that's marked, then the next block is also marked. And then the next block, and the next block, and the next block. And I can use those two claims to imply that every block is actually marked. If the first one's marked and every next block is marked, well, then all the blocks are marked. So that's what we're going to do with this principle of mathematical induction. Mathematical induction. It's going to be a new style of proof that we're going to do. And in order to do mathematical induction, we're going to have two steps. We're going to have the basis step, and we're going to show that whatever statement we're working with is true when n is equal to 1. Our domain of discourse here is positive integers, which are 1, 2, 3, etc. So we're going to show that it works for block 1, so to speak, or that the first case is true, the base case is true. That's our basis step. Our inductive step is going to include our inductive hypothesis. And that is, we're going to assume that S of n is true. And then that means that the next one is also true. S of n plus 1 is true. So we are going to assume that S of n is true. And then we're going to show through algebra or set notation or whatever kind of situation we're dealing with that the plus 1 case is also true. And then by this principle of mathematical induction, S of n is true for the entire domain of discourse. So let's see what that looks like here in example 1. I want to use induction to verify that 1 plus 3 plus 5 plus ... plus 2n minus 1 equals n squared for all n greater than or equal to 1. So I'm going to do my basis step. In my basis step, I want to show that the equation is true for n equals 1. So I'm going to say let n equal 1. Then this is 2 times 1 minus 1. Is that equal to 1 squared? This is the left-hand side. This is the right-hand side. We're going to do a lot of left-hand side, right-hand sides in here. My left-hand side, 2 times 1 is 2, minus 1 is 1, and 1 squared is 1. So it is true. So my basis step is complete. That my base case is true. So I'm ready to move on to my inductive step. And this is the step where the magic happens. We get a little bit more involved. I'm going to assume that n is greater than or equal to 1, and that this thing is true right here. 1 plus 3 plus 5 plus dot dot dot, whoopsie, plus 2n minus 1, my gosh, minus 1 is equal to n squared. This thing that I'm assuming right here, this is called my inductive hypothesis. Inductive hypothesis. And what I'm trying to do is I want to show that 1 plus 3 plus 5 plus dot 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 plus 2 times n plus 1 minus 1 is equal to n plus 1 squared. So I replaced all of these, both of these n's, there's only 2 of them, with n plus 1. So I want to show that this is true. So let's think about how we're going to attempt to do that. Let's simplify this a little bit. This was going to be 2n plus 2 minus 1 is 2n plus 1. That's 2n plus 1. And how am I'm looking at this sequence, how am I getting from one step to the next? To go from 5 back to 3, it looks like I'm subtracting 2. To go from 3 back to 1, it looks like I'm subtracting 2. So it looks like I'm adding 2 as I move this direction, or you can think about it as I'm subtracting 2 as I move this direction. So what I'm interested in is I want to know what's the term right before this last one. Well, if I would subtract 2 from this, I would get 2n minus 1. So the term right before this last one is 2n minus 1. And that should look a little bit familiar. Now this whole thing, all the way up to this term, not including the last one, looks very much like that. So my left-hand side is equal to 1 plus 3 plus 5 plus dot 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 plus, here's my 2n minus 1, second to last term. My last term is 2n plus 1. And that's equal to n plus 1 squared. Or at least I'm hoping to show that that's equal to n plus 1 squared. I'm not going to write that right now because I'm just talking about my left-hand side. So I'm trying to show something about my left-hand side. So this whole thing, like I said before, is the left-hand side of my inductive hypothesis. And that's really basically the strategy of all these induction problems, is to write out what you want to show and try to figure out what part of that is your inductive hypothesis. You want to try to make part of this left-hand side into the left-hand side of your inductive hypothesis. Because what I'm going to do next is this. I'm going to say this right here, by my inductive hypothesis, the left-hand side is equal to n squared, and that's this n squared right here, is equal to n squared plus 2n plus 1. And that's from right here. Am I using enough colors? Plus 2n plus 1. And now if I look at this, I think I can factor this. N squared plus 2n plus 1. That factors, this is factoring n plus 1 squared is n squared plus n, that's 2n plus 1. Well, hey, and that should look familiar. That is the right-hand side from right here. So I've actually shown the thing that I wanted to show. Thus, the principle of mathematical induction tells us, I'm not going to write that whole equation again, I'm just going to say the equation is true for every positive integer. And there's my little tombstone. End of my proof. And that is induction. Basis step, inductive step. The key to the inductive step is to write out what you want to show and then try to find a piece of that what you want to show in the left-hand side of your inductive hypothesis. So let's do another one. This is example 2. Use induction to verify 1 times 2 plus 2 times 3 plus 3 times 4 plus dot 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 plus n times n plus 1 is equal to, n times n plus 1 times n plus 2 over 3 for n is greater than or equal to 1. Starting off here with our basis step. In my basis step, I'm going to let n be 1, and then I'm going to write out what this is. So I'm going to use the n's here and fill those in with ones and make sure that this equation holds true. 1 times 1 plus 1 is equal to 1 times 1 plus 1 times 1 plus 2 over 3. So this is 1 times 2 is equal to 1 times 2 times 3 over 3. These 3's cancel out, and I get that 2 is equal to 2. So it is, my basis step is complete. My base case is true. I've shown that. So now I'm ready for the next step, the inductive step. Inductive step. I'm going to assume that n is greater than or equal to 1, and I'm rewriting my equation here. 1 times 2 plus 2 times 3 plus 3 times 4 plus dot 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 plus n times n plus 1 is equal to n times n plus 1 times n plus 2 over 3. And this is my inductive hypothesis. So I'm going to highlight this. I'm going to be looking for that guy. I want to show, I'm going to use another color here, that 1 times 2 plus 2 times 3 plus 3 times 4 plus dot 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 plus n plus 1 times n plus 1 plus another 1 is equal to n plus 1. N plus 1 plus 1 is n plus 2, and n plus 1 plus 2 is n plus 3 over 3. So this is what I'm trying to show. Maybe I'll write this one in green because I'm going to attempt to use colors here. We'll see how it goes. N plus 1, n plus 2, n plus 3 over 3. Okay, so we're going to start off with our left-hand side. The left-hand side is, well, let's think about what I'm wanting to show. What is going to be, how do I get from one term back to the next one? It looks like I'm subtracting 1 from each of these numbers. 1 times 2. So to go from 2 times 3 back to 1 times 2, you take 1 away from the 2 and 1 away from the 3. And I'm seeing that pattern here as well. So as I go back this direction, the term right before this is going to be n and n plus 1. Which, again, that looks a little bit familiar. 1 times 2 plus 2 times 3 plus 3 times 4 plus dot 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 plus the second to last term, n times n plus 1, plus n plus 1 times n plus 2. So this is my left-hand side, and this here, second to last term on back, is my inductive hypothesis. By inductive hypothesis, the left-hand side is, now I'm going to be substituting, instead of this yellow thing, I'm going to put in this pink thing. N times n plus 1 times n plus 2 over 3 plus n plus 1 times n plus 2. And now I'm going to do a little bit of algebra here to try to figure out, to see if I can get this purple thing that I have here to turn into this green thing. So I'm going to multiply this by 3 over 3. That way I can add these fractions together. In order to add fractions, you have to have a common denominator. So I'm going to work on that. Let's see. I'll come down here. So n times n plus 1 times n plus 2 plus 3 times n plus 1 times n plus 2 all over my common denominator of 3. And now it looks like I've kind of got an n plus 1 and n plus 2 and another n plus 1 and n plus 2. I can actually factor that out, and I'm going to be left with an n plus 3. So n plus 1, n plus 2 is what I factored out, and then what I'm left with is an n plus 3 over 3. Oh, and look at that. That is the right-hand side, my green side. Isn't that nifty? So that means I'm pretty much done. I'm just going to write my last statement here. by induction, you could say the principle of mathematical induction, but that's a lot to write. I'm just going to say by induction, the equation is true for all n greater than or equal to 1. End of my proof. Okay, let's do another one. We're just going to roll right through. I think we're going to do a total of 4 induction problems. So here is our next one. I want to use induction to show that if r is not equal to 1, a times a plus a times r to the first power plus a times r squared plus all the way up to a times r to the n power is equal to a times r to the n plus 1 minus 1 over r minus 1 for n is greater than or equal to 0. Here we're seeing something slightly different, and that's okay. We'll see how that shows up in our basis case. One thing to note here is that it's telling me that r cannot be equal to 1, and that's because if r was 1, this right-hand side would be have a 0 in the denominator, and we can't have that. So that's why we see that extra restriction there. Alrighty, so my basis step for this one is going to be slightly different, and that's because we're looking at n being greater than or equal to 0 instead of greater than or equal to 1. So for my basis step, I'm going to let n be 0, the smallest case, and then I'm going to have a times r to the 0 plus 1 minus 1 over r minus 1. I guess I forgot this is the right-hand side. I'll just do them backwards, I guess. A times r to the 0 power. Anything to the 0 power is 1. So this is 1, which means that side is a. Let's see, in this side, r 0 plus 1 is r minus 1 over r minus 1. Look at that. I can cancel out these r minus 1s, and I get that a is equal to a. So here we're seeing this is true for our basis step. Now we're ready for our inductive step. We are going to assume that n is greater than or equal to 0 and that this equation is true. A plus AR1 plus AR2 plus all the way up to ARn is equal to A times Rn plus 1 minus 1 over r minus 1. I'm going to put it over here. R can't be 1. I want to show that, let's see, A plus AR1 plus AR2 plus all the way up to ARn plus 1 is equal to A times Rn plus 1 plus another 1 is n plus 2 minus 1 over r minus 1. And we'll look at the left-hand side. The left-hand side, and I'm going to try to figure out what is the second to last term. It looks like to go from terms and going backwards, you're just taking 1 off of r. So this term is going to be ARn, just ARn. n plus 1 minus 1 is ARn. A plus AR1 plus AR squared plus all the way up to plus A times r to the nth power plus A times r to the n plus 1. And here I'm seeing this, which is my inductive hypothesis, or it's the left-hand side of my inductive hypothesis, by inductive hypothesis. My left-hand side is A times r to the n plus 1 minus 1 over r minus 1 plus A times r to the n plus 1. And I'm going to try to show that this is equal to that green thing. So I'm going to do a little bit similar to what I did last time. I'm going to multiply this by r minus 1. That way I can add these together. So this is, let's see, A times r to the n plus 1 minus 1 plus A times r to the n plus 1 times r minus 1 over r minus 1. And maybe I'll come over here. This is equal to, I'm going to factor some things out. I'm going to factor out, I think I can take out an a and an r minus 1 on the bottom. So I'm going to write that off to the side. And then look at what I have left over, which is a to the n plus 1, oops, sorry, r to the n plus 1 minus 1 plus r to the n plus 1 times r minus 1. Okay, now I think I'm going to do a little distribution here. So I've got a over r minus 1, and then r to the n plus 1 minus 1, and then I've got r to the n plus 1 times r to the 1. I'm going to add these exponents together, so I'm actually going to have r to the n plus 2, r to the n plus 2, and then this is going to be minus r to the n plus 1. And now I'm seeing some good stuff is happening. This is going to cancel off with that, and I'm going to have that left over inside. So I'm going to come down over here. I'm running out of room. This is a over r minus 1 times r to the n plus 2 minus 1. Oh, and that is actually, I could write that up there. So that is basically my right hand side. So I've done it with just enough room to spare. By induction, the equation is true for n greater than or equal to 0. Okay, I think we're ready to move on to the last one. Example 4. Use induction to prove that 3 to the nth power plus 7 to the nth power minus 2 is divisible by 8 for all n greater than or equal to 1. Maybe do an aside. For something to be an even number, that means it's divisible by 2. So we could write it as like 2k. For something to be divisible by 8, that means we could write it as 8k. 8 times some integer where k is an integer. So that's what we're going to be looking for in this one is, can we write it, whatever we're looking at, as 8 times something else? So keep that in mind as we start this proof. Starting off with my basis step. In my basis step, n is going to be equal to 1, then 3 to the first power plus 7 to the first power minus 2 is, let's see, 3 plus 7 minus 2 is 8, which is divisible by 8, of course. 8 is divisible by 8. So that is my basis step. This one is a little bit different than the last one in that we're not looking so much for equations. We're looking for this divisible by concept. This 8k is what we're going to be shooting for. All right, inductive step. Assume that n is greater than or equal to 1 and that 3n plus 7 to the n minus 2 is divisible by 8. What I want to show is this. I want to show that 3 to the n plus 1 plus 7 to the n plus 1 minus 2 is divisible by I keep writing divisibly by 8. So this is divisible by 8 is like the right-hand side of the equation from the last one. That's why I wrote it in green. Okay, here we go. So I'm going to go back to my induction hypothesis. Because 3n plus 7n minus 2 is divisible by 8, by definition of what it means to be divisible by 8, 3n plus 7n minus 2 is equal to 8k. For some, maybe I'll use m, since I'm using n. For some m that's an integer, m is in z. So let's work on this a little bit. I'm going to do some rearranging here. I'm going to subtract 7 to the n and add 2 to both sides. And I'm going to write this as 3n is equal to 8 times m minus 7 to the n plus 2. So I'm going to come back to that. And I'm going to come back over to 3 to the n plus 1 plus 7 to the n plus 1 minus 2. I could write that as 3 times 3 to the power n. So this is a 3 to the first. So when you multiply two bases, you add their exponents. So I'm breaking up this n plus 1 into a 1 and an n. And I can do the same thing with the 7. Plus 7 times 7 to the n minus 2. The reason that I want to do that is because I know something about 3n. I know that 3n can be written as this other thing. And I'm going to plug that other thing in there. So this is equal to 3 times 8m minus 7 to the n plus 2. And then I have the rest of this, plus 7 times 7 to the n minus 2. And I'm going to do some distribution here. 8 times 3 is 24m minus 3 times 7 to the n plus 6 plus 7 times 7 to the n minus 2. And now I think I can combine some like terms. Let's see, this is a like term with that, 3 and 7. This is a like term with this. So I've got 24m minus 3 and 7 is plus 4 times 7 to the n plus another 4. Okay, so I'm looking for things that I can write as 8 times something. So I can write 24 as 8 times 3, 8 times 3m. I can factor a 4 out of this one, these last two terms, and write that as 7 to the n plus 1. So this term right here is already divisible by 8. Is this term divisible? Well, this term is divisible by 4. What I really need to know is this an even term? Is that term divisible by 2? Because if this is divisible by 2, then I can, whatever that 2 is, can come join this 4 and turn into an 8. So now I kind of have a new goal for the direction of my proof. Is now I want to show that 7 to the n plus 1 is divisible by 2. Well, let's think about this. If 7 is odd, then 7 to the n is 7 times 7 times dot 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 times 7. There's n copies of 7 here. So this number, multiplying an odd number by itself is odd. I think we proved that. Oh, I'm not going to be able to remember which proof it is, but I think we proved that one already together in class. So when you if n is odd, n times itself is also odd. And so I'm just doing that a bunch of times, multiplying odd numbers by themselves, so that's odd. So if 7 to the n is odd, and you add 1 to that, then you get something that's even. So 7 to the n plus 1 is an even number. So if 7 to the n plus 1 is even, it's divisible by 2. Thus, 24m plus 4 times 7 to the n plus 1 is divisible by 8. By induction, 3n plus 3 to the n plus 7 to the n minus 2 is divisible by 8 for all n greater than or equal to 1. So the style of these induction proofs is write the base case, which is the very first step. It's the very first block on the table. And then we're going to show that it's true for the next block. If it's true for the n+1 case, I don't have to show, it's really difficult to show that it's true for every single case. But if I can always show that it's going to be true for the next one, and the next one, and the next one, the +1 case, then it'll be true for all the values in my domain. That's kind of the style of these induction proofs. And that is the end of this section. And I will see you next time.